In this video, we introduce Sungkhan Chang's solution of problem B1 of 2014 Putnam competition. A base 10 over expansion of a positive integer n is an expression of the form shown in the second line. In this expansion, the coefficients di are allowed to reach 10. For example, 10 can be written in two different over expansions. One is 10 times 10 to the 0, and the other is 1 times 10, plus 0 times 10 to the 0. The question is to describe all positive integers that have a unique over expansion. Here are more examples where we don't have a unique over expansion. Let us use capital A to represent the digit di, being 10. It is convenient notation for the following demonstration. Also, let us use parentheses and commas to denote a number with over expansion digits. For example, 210 is denoted by 2, 1, 0. From left to right, if we have a non-zero digit di, followed by 0, we can always come up with a different over expansion. Since di is at least 1, we can use one copy of 10 to the I, and write it as 10 times 10 to the I minus 1. And this will occupy the place of 0 times 10 to the I minus 1. So the two new digits are di minus 1 and a. The pairs of two digits are different, while they represent the same numbers. Let's get ourselves used to this carryover. Remember that it is about one non-zero digit followed by 0, to the right. If we have 10, the first digit 1 goes down by 1, becoming 0, and the 0 digit becomes a. If we have 20, the first digit 2 goes down by 1, becoming 1, and the 0 digit becomes a. For 700, focus on 70. Then it is equal to 6a, and hence, 6a0. For 5000, focus on 50. Then it is equal to 4a00. If we have several zeros, like 5000, we can keep doing this. Focus on a0 in the middle of 4a00. Then 1 less than a is 9, and so we have 9a in the middle. And now we have 49a0. We still have 0 at the end. So a0 changes to 9a, and we have 499a. This one is more interesting. We see 0 in 5103, and we change it to 50a3, as done before. But it generated 0 in the second digit from the left. So we can change that 50 to 4a. Here it is. We were using 0 digits, and if we don't have 0 digits in the usual expansion, we can't do this method. We have to ask ourselves if there can be other methods that we don't know about. Remember, in mathematics, we can sometimes prove that there cannot be anything we have not discovered. After you play around a little bit, you will be convinced that there can't be any more. I would like to put it this way. One's failure cannot be a proof of impossibility. When we make a mathematical statement, we make sure that it is absolutely correct, and other trained people understand it as well. If we stick to the usual expansion, not over expansion, we won't have a in the digits, and we claim that this statement is correct. A positive integer n has a unique over expansion, if and only if all digits of the usual expansion are non-zero. This direction is relatively easy to prove. If a positive integer n has a unique overexpansion, then all digits of the usual expansion are non-zero. Let us use the method of proof by contradiction. Suppose that there are 0 digits in the usual expansion. Since it is a positive integer, there must be a non-zero digit to the left of a block of 0 digits. Let di be that digit. Di is positive, and not a, since it is in usual expansion. Now the carryover method introduced earlier allows us to change that usual expansion to an overexpansion. Remember, a usual expansion counts as an overexpansion. Hence it contradicts the assumption that n has a unique overexpansion. This concludes the proof of one direction. Let us state the other direction. A positive integer n has a unique overexpansion if all digits of the usual expansion are non-zero. Let us remind you that vigorous assertion does not make a proof. We can't just say that it's not possible because we thought about it. We have to be more convincing for those who don't see this as obvious. We shall use induction on n. The base case is when n is equal to 1. We use di for digits of an overexpansion of n. The top digit dk contributes as dk times 10 to the k, and n must be greater than or equal to dk times 10k. As the first digit of overexpansion vary from 1 to 10, it must be greater than or equal to 10 to the k. All these are less than or equal to 1, and hence k must be 0. So dk is d0, and d0 is 1. It is tempting to sneak in the proof of vigorous assertion here, saying n is small. I checked it, it can't happen. Since we decided to avoid this kind of assertion, I tried an approach that is more conclusive. We proved that any overexpansion must be equal to the usual expansion, and this proves the uniqueness of overexpansion for n equal to 1. Suppose we have an overexpansion of n, and suppose that the general statement we want to prove is true for all positive integers less than n. I apologize about the typo here. The induction hypotheses must be, the general statement we want to prove is true for all positive integers less than n. The condition of the general statement is that all digits of the usual expansion of n are non-zero. So ak vary from 1 to 9. This is the reduction step, so we can use the induction hypothesis. ak are from the usual expansion, and dk are from the overexpansion. We set aside a0 and d0. Since each term in the summations in both sides has a factor of 10, if we consider the congruence relation modulo 10, we have a0 congruent to d0 mod 10. Since a0 is positive, the maximum absolute value of d0 minus a0 can be as follows. When a0 is 9 and d0 is 0, or when d0 is 10 and a0 is 1. For both cases, the absolute value is less than or equal to 9. The absolute value is congruent to 0 mod 10, and 0 is the only number in 0 to 9 that is congruent to 0 mod 10. Hence a0 minus d0 is 0. By cancelling a0 and d0, we enter a number less than n, since a0 is positive. However, it is equivalent to having 0 at the right-end digit, and we cannot apply the induction hypothesis, since the usual expansion contains 0 digit. Thus we further divide both sides by 10. Then the summations at the bottom line becomes a number with usual expansion, where there are not any 0 digits. The summations at the bottom line can be viewed as 2 over expansions of a positive integer less than n. Hence by the induction hypothesis, each ak and dk are equal to each other, and the numbers of terms in the summations are equal to each other as well. This concludes the whole proof, since we proved that any overexpansion must be equal to its usual expansion. Thanks for watching.